Hey guys, today we're going to be looking at sorting and searching. To start off with, we're going to take a look at sorting. So the most important thing about sorting is knowing how to pick which algorithm should be used in which situation in your interviews. But before we can go over how to pick an algorithm, let's quickly review the sorting algorithms that are available. For O of n squared algorithms, we have bubble sort, insertion sort, selection sort. And although these algorithms are reasonable at performance for small inputs, they become incredibly slow for large input sizes. Next, with a slightly more efficient type of algorithm, we have O of n log n, which are the most efficient a comparison-based sorting algorithm can be. As examples, we have merge sort, heap sort, and quick sort. Each of the O of n log n algorithms has its own benefits and drawbacks, but one of the main ones to be aware of is that quicksort can have an O of n squared worst case runtime. And finally, we have O of n algorithms, like counting sort, radix sort, and bucket sort. Now, don't worry if you can't remember all of these algorithms, but at least remember the general idea of each algorithm type. O of n squared involves comparing each element to close to all of the other elements. O of n log n manages to speed this up by using a divide and conquer strategy where it repeatedly splits the problem into smaller, easier to solve problems. And O of n forgoes being comparison-based at all, instead opting to use counting to sort the array. Now let's look at some key terminology used with these sorting algorithms. A stable sorting algorithm is a sorting algorithm in which elements that have the same value in the unsorted array will appear in the same relative order in the sorted array. One example of a stable sorting algorithm is merge sort. Additionally, be wary of thinking that since counting sorts are O of n runtime, they are always the best option. First, these types of sorts only work on data that can be counted, like integers, and will not work on data that can only be compared. And do remember that O of n ignores some other factors. In reality, it's actually O of n plus k, where k is the number of possible values that each element of the data set can take on. If k is large, k can actually become greater than n log n, making this supposed O of n sort actually worse than O of n log n. Let's look at a quick example to understand how that can happen. If we, for example, had an array that was only of size 10 of integers, but the integers could be anywhere between a value of 0 and 1 million, our O of n sort is actually 10 plus a million, which is by far worse than what our comparison-based sorts could do. So you have to really be careful and know a lot of information about your data set to reliably use an O of n sort. So next, let's talk about space requirements for sorting algorithms. So in terms of space requirements, the terminology you want to know is an in-place sorting algorithm. And when a sorting algorithm is in place, it means that it only uses O of 1 extra space. So some algorithms actually do, in fact, use more than O of 1 extra space. One example is merge sort. And merge sort uses O of n extra space because it has to make a copy of the array to perform merging. That's actually one of the main drawbacks of merge sort. So how will sorting actually be used in your interviews? It's most likely that you won't get a problem where all they're asking you to do is to sort some data and implement a sorting algorithm. Most likely you'll need to use your sorting knowledge to either simplify a larger problem or improve the time complexity of some already existing solution to a problem, or to improve your own solution to that problem. And additionally, don't code a sorting algorithm unless that's explicitly the question. Your standard library for your programming language should have some way of doing sorting. So don't waste time or the potential for making errors on a sorting algorithm when unnecessary. All right, so now let's take a look at an example of how this sorting can actually benefit you in problem solving by taking a look at a question. So the question we're going to look at is the k smallest elements question, where your goal is to find the k smallest elements in an array, meaning either the one smallest element or the two smallest elements in the array or three of the smallest elements in the array, etc. So One of the ways you do this, if you aren't using sorting, is you find the first smallest element by doing a single pass through the array in O of n time and tracking the minimum element in that iteration. Then, if k was 2 instead of 1, you would have to do an additional pass in O of n to find the second smallest element by, again, tracking the minimum element that is larger than that first smallest element, and so on and so forth for 3, 4, 5, overall resulting in an algorithm runtime of n times k. However, if you want to make this quicker, you can actually go ahead and sort the array in some cases, because sorting the array is going to only take O of n log n time. It doesn't matter what k is, because to find the k smallest elements in a sorted array only takes a single pass through the array, just grabbing the elements at either the start or the end of the array, depending on whether you sorted it in ascending or descending order. Now, the reason why this O of n log n algorithm might be better than the O of n times k algorithm is k could actually be larger than log n. And an example of where this can happen is if you need the 15 smallest elements in an array of size 1000, it's already faster to sort the array than it is to do 15 individual passes. So next, we can move on to searching. So with searching, we're going to split the algorithms into two main categories. When you're looking at arrays and lists, you have linear search and binary search. And when you're looking at graphs and trees, you have breadth first search and depth first search. Now, all of these searching algorithms are very important for you to know going into technical interviews, since you may be asked to solve a problem that is either solved using one of these algorithms exactly or forcing you to modify one of these algorithms to suit the specific need of the problem. I won't go into the details of each algorithm here, but you can find great supplemental resources on either YouTube or the internet to give a clear and concise depiction of these four algorithms that you most definitely should know how to implement. Now, one thing to keep in mind with searching is that the data you are provided may not always be in the right format to search through immediately. For example, you may want to change your data somehow in order to make searching more feasible or quicker. An example is that if you want to search an array with binary search, you have to actually have it sorted beforehand. And that allows you to find elements in O of log n rather than O of n if you're willing to take the time to sort the array first. Another example is that if you need to check for membership, you can do it with a hash table in only O of 1, which could also be considered a type of search. And another example is that data can be pre-processed in a lot of other ways that aren't necessarily just sorting or putting into a hash table. For example, if you want to compute a rolling sum of an integer array, that can be computed in O of n, and then it makes it easier to search for things like the difference of numbers that were in that array. So a theoretical example, just to illustrate the fact that pre-processing or changing data around is actually oftentimes worth it for searching, is if we say that the naive searching approach takes O of n cubed, but we can pre-process the data in O of n squared and then solve it in O of n squared using that pre-process or the addition or the change in data structure, then we're actually managing to solve the problem a lot quicker in an overall O of n squared rather than O of n cubed solution. So now we're going to take a look at an example of how a searching algorithm can work by processing the data, by doing a bit of processing on the data. So the algorithm we're going to look at is an algorithm for finding substrings, which is something that's usually included in the standard library of programming languages, but can be very interesting to take a look at how it's actually implemented. So first, we need to frame the problem, which requires defining some terms. Specifically, we're going to look at the string that we are searching within will be called the haystack of size m, and the substring that we are searching for will be called the needle of size n. So then the naive solution for a search is for each character in that haystack, we go ahead and search to see if that character and the following characters match the needle. which means that for each of the m characters in the haystack, we have to do, at worst case, n comparisons to check if it matches the needle, which is an O of m n complexity. So one of the ways that this complexity can actually be reduced to be better to only m plus n is by computing a rolling hash. Now, the worst case for this algorithm is still O of m times n, but that's only a worst case if there's a bunch of hash collisions, which can, in fact, be avoided with a good hashing algorithm. So now to explain how this actually goes about making the searching process better. The first thing to do is to pre-compute the hash of the needle, that is, the substring we are searching for, which only takes O of n. And then a rolling hash, basically a hash in which we only have to compute the parts of the hash at each character that we check, can then be used to check the rolling hash of the current part of the string that we're looking at with the needle, and that is an O of 1 check because the hash is being computed. It doesn't have to compute everything at once because it's just a rolling hash. And then, because we've managed to do that, we only need that initial O of n plus that O of 1 for each of the m elements, which then goes ahead and gives us an O of m plus n search. So if you have any further questions about sorting and searching, please feel free to follow up about anything in class.